Okay, good evening. This will be our second class for the week, and we'll continue our discussion on memory and context management in AI agents. Um, in our earlier class, our class earlier in the week, we talked about why agents need external memory. We talked about in context and persistent memories. And we also talked about the taxonomy for persistent memories, where we talked about semantic memory, which has to do with facts and general word knowledge, episodic memory, which has to do with the agent's own experience, as in the um, what has happened as the agent executes, keeps the records of that, and procedural memory, which has to do with workflows, procedures, and so on. So today we are going to go into a bit more detail, starting with semantic memory. Um, semantic memory, we are going to look at two categories. We'll look at vector-based and knowledge graph-based memories. So to talk about vector-based memory, it's first important to understand vector embeddings. Now, earlier on in the course, we had explained that LLMs don't understand text the way we do, that they operate on number representations of natural language text, and they operate on tokens, and these tokens are represented as numbers. So each token is converted into an array of numbers, and this is done in the LLM's embedding layer. It's these arrays of numbers that um, the LLM processes to predict the next token of its output. So it keeps predicting the next token until the predicted next token is an end symbol, in which case it can output um, the entire predicted um, output sequence, which is what we Okay, sorry about that interruption. Um, I was talking about how the tokens of text that I impute to the LLM get converted into um, vectors of numbers in the LLM's embedding layer, and that the LLM processes these vectors to predict the next token in its output, and it keeps reading the next token until that next token becomes an end of sequence symbol, at which point we get the full output of the LLM. Of course, this gets tokenized. It was the words that we read from the LLM's output. So, an example of this word or token to vector conversion is what I have here, where the word apple gets converted to a vector like this, and the word banana gets converted to a vector like this. One important thing here is that in vector space, um, in vector space, words that the vectors representing words that are similar in meaning gets to close to each other in vector space, so that you could find clusters of vectors, which those clusters are vectors for words whose meaning are close to each other, words that share a domain. And so that way, it's how similar two words are can be determined by how close they are, how close their vectors are in the vector space. So this clustering enables makes it easy to do what is called fuzzy search in Agentic. It's fuzzy in the sense that you don't follow complete logic. You just, if it's fast, it's similar, you don't follow through the entire logic chain, or something like using heuristics. Heuristics is somewhat fuzzy logic, right? For example, if you are looking for um, orange, but orange is not available um, in that um, vector space, you could get something similar to orange, maybe tangerine. It's quite close, right? And it could become it's close enough that it could say, well, depending on the use case anyway. Now, a common measure, like I talked about how similar two words are in meaning, can be determined by how close their vectors are to each other in vector space. And one way to um, quantitatively measure this is cosine similarity. And the cosine similarity can be calculated as it's just the cosine of the angle between those two vectors. This is now a bit of mathematics. So the angle between those two vectors, its cosine gives the cosine similarity. And one way to calculate that would be by dividing the dot product of those two vectors by the product of their magnitudes, as I've shown here. Now, the question is now, what are the limitations of vector-based memory, where you have only use only vectors in your semantic memory? Um, Now, vector-based systems, they are very good for correlation. I mentioned about similarity in vector space, which is indicated by how close the vectors for two or more words, their vector representation, how close they are in vector space. So vector-based systems make it they are really useful when we want to perform correlation, but they do not lend themselves well to exact logic. As we go further, we'll see, get a clearer idea of this. Now, essentially, vector databases only capture the fact this is this, right? Bola Tinubu is the president of Nigeria. Um, Donald Trump is the president of the United States. That's just this is Anthony Okoro. That is a fact, right? But they are not able to capture the exact relationship between the exact nature of the relationship between two items of information. Just know that this is this, right? For example, okay, still the I am a trainer in CodeCamp 5x, right? It's a fact, but really, what does it mean? How am I related to CodeCamp 5x? The vector-based memory may not really understand, um, may not really capture the nature of my relationship with CodeCamp, right? Yes, it's a fact that I'm a trainer in CodeCamp, but what really does that mean? And yeah, I was giving the example of an orange and a tangerine. You're seeking for an orange, but um, orange, there's no orange in the vector database, but then there's tangerine, and so you get the result you get for your search for an orange becomes tangerine. Yeah, that might be useful in some contexts, but it might also not be useful in others, because essentially tangerine is still not an orange, even though they are closely related. Any questions so far?
So I'm just trying to wrap my understanding. I get the similarity. Um, um, how do I say it now? How similarity can be similar. I mean, how two different vectors can be similar in the vector space. But I said the limitation there is that it doesn't capture the exact logic. That's what I'm just trying to. Because I'm wondering that still like the example you give, like orange and tangerine. And yes, I know they are in the same citrus family, if I'm right. So, is there any other further logic that needs to be known again, apart from their relationship in that vector space that pertains to logic that you mentioned that can lead to
Okay.
hallucination?
An orange is similar to um, a tangerine, right?
Yes, sir.
But
Can same family kind of.
now let's assume your vector database knows that an orange is similar to a tangerine, and let's say it knows that um, an orange is similar to a lemon. These are facts, right? If an orange is
Yes,
similar
sir.
to a tangerine and an orange is similar to a lemon, is an orange is a tangerine similar to a lemon?
No, sir. They are far.
Orange is similar to tangerine.
Yes,
Orange is
sir.
also similar to lemon. So is
Yes,
orange
sir.
is tangerine similar to lemon?
Far apart.
Okay. Oh, I'll give the logic again. Orange is similar to tangerine. The same orange is similar to lemon. You had mentioned that orange and tangerine are citrus, right?
Yes, sir.
Is lemon also citrus?
Oh, yes. Sorry, I thought we were talking about is it lime? Yes, it is. I think
So
it is.
if orange is similar to tangerine and orange is also similar to lemon, it's logic that lemon has some relationship with tangerine, even though it may not be as close as its relationship with orange. I'm just using hypothetical fact. Now, with vector-based systems, you could have a fact that orange is similar to tangerine. You have another fact orange is similar to lemon. But if you don't have the fact that orange is similar to tangerine is similar to lemon, you don't you the vector based memory does not have it does not engender to discovering this relationship that is not explicitly captured, right? That's why I'm saying it does not understand. That's what I mean by it does not understand the exact logic. It doesn't make it easy to understand the nature of the relationship between these two entities, or these three entities: orange, tangerine, and lemon. Yes, it's clearly stated that orange and tangerine are related and orange and lemon are related, but it's not stated that tangerine and lemon are related. So with vector based memory, we don't have that association. When we get to knowledge graphs, we'll see how um, knowledge graphs help to improve such um, relations and exactly how it, it's inherently um how do I say inherently it's embodies exact knowledge and Um, Sorry once again. For some reason, my network connection is being a little flaky.
Okay, so I understand, sir.
A little flaky today. Let me just switch to the most stable network I have at the moment, and then we'll move it. Okay. So I don't know whether did you get my explanation, my response to your
Yes, sir.
question. Okay.
Yes, sir.
All
Thank
right.
you, sir.
You're welcome. So move ahead. So at this point, we'll just we'll look at a demonstration of vector-based memory agents with code. So that's what we've been talking about in um, a bit more perspective. So I'm stopping sharing of my screen. So um I'll share the code, my IDE, so we can run the code. Please let me know when you can see my screen.
So, all right, sir. Yes, it's off.
Okay. Um um so here we are going to the script here uses a vector um vector memory. This the vector memory is using is the FAISS. It's Facebook's implementation of similar is vector store. It's really optimized for similarity search. Um, there are other vector databases that you could use, well, like ChromaDB, or if it's in a production system, something like Pinecone. Those are better, but just using this because it's just for demonstration and it helps us to also minimize the complexities of running a full scale vector database. Okay. So here loading API keys and all that. These are the typical configuration steps that we've been using in the other scripts. Um, we are going to run with graph models, but this you're also able to use OLAMA models. If you toggle use grok to false, that means you use OLAMA models, but we're going to use grok at least until we exhaust the what do you call it? Do we exhaust the limit for it here? Yeah.
Okay.
Now we are going to use the nomic, but even though we are running um inference model on grok, our embedding model will still run on OLAMA. We're using an nomic embed text latest. You could use any other embedding model you want. Um, yeah, Grok doesn't readily have an embedding model. So
Okay, I was about to ask, sir. I
yeah,
didn't get to say, doesn't mean there's no embedding model on Grok that we can use.
it
Because, like,
doesn't
for me,
readily,
I'll be running
Grok
lab.
doesn't have a readily available embedding model.
Okay.
Yeah.
What would be the option for me, sir? That we run it fully online without no local
Well,
machine.
OpenAI has embedding models. I believe Google has too. But so it's just to you could still use, there are providers, cloud providers that have embedded models that you could use. Okay, so search to Taveli. I think we used Taveli in the um last week's class. So here we define our embeddings. So we're setting up our um, semantic memory by defining the embedding, using Olama embeddings with this special embedding model. We could also have used maybe this Llama 3.2 3B as the embedding model if we want, right? Um, yeah, and here we define the vector store here, and then we now go to the agent itself. We define the state, user queries. That's the query from the user's request. Search query is the query we'll use to search on Tavili. Research data will be the results we get from the Tavili search. Relevant memories will contain the context, whatever context we retrieve from our vector store. Of course, the ones that are relevant to the user's query. If we retrieve context that is not relevant to the user's query, there's no point adding to the state. Draft will be the draft of the report that the agent writes from the retrieved information, either information from the vector store or from the ability search. And critique will be the agent's critique of that draft, which enables the agent to um, self-correct by rewriting the draft to fix whatever issues we have flagged in the critique. And revision count enables us to avoid having an infinite loop, so that after a certain number of iterations, the loop can terminate. And then we define our nodes. Memory lookup node, it allows us to retrieve relevant context from the vector store if available. And here we're defining a default similarity threshold. Yes, when we get further down in the code, we see that there's a config. In the config, we specify the threshold above which we consider a retrieved context to be relevant to the user's query. But this default similarity threshold is just assuming that is not defined, that threshold is not defined in the config, then it uses this default. And so here we search the vector store, we perform a similarity search for the user's query. So we try to retrieve information from the vector store that has similarity to the user's query, and we retrieve K here specified how many results do we want to retrieve. So here we just want the top one result, the result with the highest similarity score. If we specify it to be 3, that means we want the top 3 results, top 3 in sense of the one that have the top 3 similarity score. And so the results will contain the actual information and its similarity score to the user's query. And so essentially, whatever we retrieve, we check, does this similarity score, is it greater than or equal to the threshold we determined? If it is, then we consider it to be relevant to the user's query. But if it's not, then it's not relevant. So if it's relevant, we just print it out. This is just to enable us have more better observability into what is happening as the agent executes. But this print is really not necessary um, as we need to in production. But since we are using this as a demonstration in class, that's why I added these prints. In production, instead of print, you would typically use a logger. You would typically log that if you need it. Anyway, it's good to log at least keep it for some period in case of failures, so that it allows you to troubleshoot. And if we determine that the retrieved information is relevant, we return. Now, we are using an edgeless graph, right? So that's why we're returning a command object where we're updating the relevant memories in the state with the information that was retrieved, and the next node will be the writer node. But if we don't find information from the vector store that's relevant, then we just we now execute a search on using Tavili, and that's why if in that case the next node will be researcher, and we update relevant memories to be an empty string, and the search query becomes the user query. Set the search query to the user query. Now the research node essentially just calls search to, which is Tavili search, with the search query, and we retrieve the results, concatenate them as a string, and then we update the research data in the state with that information that was retrieved, and the next node is the writer node. Either way, between the memory lookup node and the research node, we expect to have retrieved the information needed to write the reports that will be output to the user by the agent. Then in the writer node, we have this web prompt that essentially asks the LLM to synthesize the information that's retrieved from the vector store, of course, relevant information, synthesize it with the information that was retrieved from Tavili search to synthesize this into a concise report. And it specifies that the information used in the report must be from reputable sources, and that the report should cite those sources, including the URLs in the list of references, as even it was able to retrieve any URL. And it also says if there is a critique, then the LLM should address that critique in the draft it's writing. This part is important when the agent is doing a reflexive loop in which it's trying to autocorrect itself. It's trying to, after it critiques the draft, it tries to modify it to handle whatever issues were flagged in the critique. And so we just invoke the LLM with the relevant information from the state, and we update the state with the draft, which is what the report, current draft of the report, and the next node will be the critique node. The critique node essentially just the prompts for the critique node essentially just asks the LLM to go through the current draft of the report in the context of the user query, I would say, and then to determine whether the draft correctly and accurately and completely answers the query, and then it provides a critique of the draft in which it outlines the specific strengths and shortcomings of that draft, and um, it also makes a call whether it's necessary to perform another web search, assuming that the current information available, both the context retrieved from the vector store and the information retrieved from the web search, whether they are sufficient for generating the requested report. So if they are not, it's supposed to indicate, hey, you need to make another website search. But if they are adequate, then you don't need to search again. And then the fourth question is for the LLM to determine whether the search query that was used, I mean, is there a better search query? There's a search query that would likely provide a better, retrieve better information for writing this report. So if there is, then it should um, suggest that search query. And the LLM is supposed to return output a JSON in this schema. Is current draft adequate? That's a Boolean. Was the critique? It writes its critique of the current draft. It states whether or not the current draft is necessary to perform a new web search. This is a Boolean, and then it suggests a more appropriate, a more optimal search query. So now we execute that. Well, we create a chain where we pipe the LLM's output to a JSON output parser, and we evaluate, invoke that chain with the prompt, and then based on the output, if the JSON output of well from the LLM after it's been passed, if it indicates that the current draft is adequate, then we should just save that draft into the vector store so that in subsequent queries, if it's relevant to the subsequent queries, it can be used as information for responding to those queries without the need to perform a website. If, on the other hand, the revision count that's from the state, if the revision count is greater than our specified maximum revision, this is what we provide in the config. If it's beyond it, then if it's more than that specified maximum revisions, then we should also terminate the execution, the agent's execution loop, and use whatever drafts we have as the final output. This helps to ensure that we don't get into an infinite loop situation. But if neither of these conditions are met, then we update the state with we increment the revision count, and we update the search query to the suggested search query as output by the LLM. And then now, if the JSON output indicates that it's necessary to perform a web search, then we go to the researcher node where we now search on Tavidi again with the suggested search query. But if it's the LLM thinks that it's not necessary to perform another website, that means it has adequate context to write the report. It can still address the issues flagged in the critique based on the context it already has. then we go back to the writer node. Either way, we've already looked at the researcher and writer node. So for the memory node, save memory node is where it now persists the current draft, which in this case would be the final draft, because it's only when it has achieved the final draft status, either because the LLM, the critique has LLM has looked at the draft and it thinks it's okay, it's good to go, or there has been more revision attempts than the specified maximum, in which case it stores the current draft, persists in the vector store, and of course outputs it to the user. So here we just create a document containing the current draft. Of course, we also here we are putting the topic as the user query and knowledge as the current draft. And then we provide metadata, essentially that the source will be agent output, so that whenever this is retrieved, the LLM can know that this was the information was gotten from agent output. Well, you can provide other metadata as your use case requires. Add this document, we just persist it in the vector store, the FAISS vector store that would define. This print statement is just to, this one is just for us to know that the information has been persisted in the vector store successfully, and then it outputs that final draft for the user, of course, and the loop ends. And here we now build the graph. Of course, it's an edgeless graph, so we just need to define nodes and then specify the start, that the execution starts from the memory lookup. We compile the graph and then we execute. Now for execution, we are going to, I talked about max revisions, and I talked about similarity threshold. This is where they are defined in the config. We're in the execution here, we're using a synchronous function, because the methods of we're using to evoke the graph is just asynchronous for a stream, asynchronous stream method of land graph. So for the first run, we'll just ask what the query is, what are the latest developments in AI as of December 2025. In the second run, ask about the different thing. What were the developments in quantum computing in 2025? And in the third run, we now ask something similar to what we had asked before. It simply says, tell me about the developments in AI as of 2025. Essentially more like a rephrasing of the first query. And it's expected that at this third point, the LLM would use the information it already had from the first query that it persisted in the vector store, instead of now going to perform a targeted search again. So we run the scripts now. So the expectation will be for you to also run this script yourself and try to run it with different input queries, so that you see when it uses, it directly goes to, okay, let's look at the outputs from this run. Now the first run, I mean, this is the first time, so the memory is just empty. So when you go to the retrieval node, definitely you can't have any relevant memory since nothing has been saved in the memory. So relevant memory is nothing. Search query is the same as the user query. And so it goes straight to the research node since it doesn't have any relevant memories. Um, the research node, this returns quite a bit of data, a bit of information, including web, the URLs of the sources. And since it has retrieved that data, the next node from our logic graph logic would be the writer node. And so he writes a first draft. After writing that draft, it will be to next node will be the critique node. The draft includes references like our prompt specified. Um, it cites the sources, including the URLs. Now, the critique node is fine with the draft. So there's no need to go back to um, a reflexive look back to the writer node or trying to perform another search. Since it's okay, we go to the save to memory node. That I don't remember the exact name we call that node, but the node that persists the um, information to our vector store, and it saves this. This is the document it saves, and it also outputs that as the final. I mean, this is the vector store key, the key in the vector store and the content, and it, of course, outputs that the content. This is just an excerpt from the content, and then it outputs that entire draft as the final report, including reference list where it cites the sources and includes the URLs to those sources, like like prompt specified. Even though there is including a note, the information in this report is based on data from reputable sources and so on. This is very unnecessary, but we could try to guide the LLM from adding such unnecessary information from the prompts, but really, for the purposes of our demonstration, this suffices. Now, in the second round, where we ask about, I think it's quantum computing, a document is retrieved, right? It, it its similarity, the similarity threshold is 0.7, and the similarity for that document is let me see, is 0.5. So it's the similarity is lower than the threshold we specified. And so the point why I want to make here is that you need to specify the similarity thresholds such that um, it helps you to filter out irrelevant um, information that you put from the vector store. Now, in this case, is this document really relevant? This is the only document that is in the vector store anyway, and it's the report that we got from the first run, right? So that's about AI and not about um, quantum computing. So it's really not is really not relevant enough. So the threshold is fine here. And so because we didn't retrieve any relevant memory, it searches on Tavili with the search query the same as the user query, just like our logic specified, and it's able to retrieve information. It goes to the writer node, drafts a report, moves to the critique node. In this case, the critique thinks that this is not adequate. It provides a critique. It says the current draft provides a good overview of the developments in quantum computing in 2025, but it lacks depth and specificity in some areas, etc., etc. That means that we are going to rewrite, the agent is going to rewrite that draft. Now, it's going back to the research node, implying that the agent thought that there is important to perform is further web search. And you see here that the suggested search query is different from the earlier search query. So it's this new search query now that will be used in the new search that the agent performs. And then with the result from that search, the writer node writes another draft. The critic still thinks that this is not adequate, and thinks that another search should be performed. The agent now loops back to performs another search, writes another draft based on that, and finally, the critic thinks that it's all fine. Well, it's also possible that this was just because, if we read through that critique, I guess if it could be that it's because he has, I don't remember the maximum retries he specified, but it could be that he has hit the maximum retries. But essentially, at this point, for whichever one of the reasons that the conditional check we have, the loop is terminating, and we the agent persists that new draft in the vector store and outputs. Well, we are printing out the final report. Of course, you could output it in some other way as you choose in your own agent. And the third run, we essentially ask the same thing as in the first run. The latest, the AI, latest developments in AI as of December 2025. Here, it retrieves the documents that we persisted from the first run with a relevance, a similarity score of 0.766, and we have specified that our similarity threshold was 0.7. So the similarity score for this document is higher than our threshold, and so the agent considers it a relevant memory, and it will thus use it in drafting the report. So it doesn't it doesn't it doesn't try to perform a search on Tavidi, since it has retrieved the relevant memory. Hence, it moves straight to the writer node, which writes the draft, and the critic node thinks, yeah, that's fine. Of course, it should be fine if his own query as the earlier one. And so it just moves on and persists that again in the vector store, and we print that out to the user. And essentially, this is how, by using a vector-based semantic memory in our agents, we are able to avoid performing on web searches unnecessarily when we have adequate information in our memory, and the with that information and from its reflexive loop mechanism, the agent is able to critique its output and refine it. And essentially, the memory helps us to optimize resource use, assuming web search. Of course, web search is there are some costs attached to it. Either you're paying the search provider or the infrastructure on which you're running your search service costs resources to run. So where you have adequate memory, adequate information, relevant information in your memory, you use that instead of trying to run external searches or use some of that tool to retrieve information that may be more expensive than the memory you already have fixed the information to. Also, this just demonstrates using vector-based memories in AI agent. Is there any question at this point before we look at knowledge graph memories? I'll stop sharing a bit and then go back to the slide while I wait to know if you have any question.
Yeah, I just want to ask her. It's in the loop when the critique, if any critique is found, that it may go back again. Is there, although I remember you mentioned the retry, may put a cap on how many. I was about asking, is it possible for the loop to run indefinitely? But at a point you mentioned maybe the retry may was more responsible for it to put a stop to it.
Yeah, of course. If you don't put a cap to the number of iterations, it will keep running. It may keep running indefinitely unless maybe you're lucky that the critique becomes satisfied with a particular iteration of the draft. If you remember, in the last, I think it was in the previous week, when we talked about conditional edges on the router, we specified that you need to specify a maximum number of iterations. And even for recursion, you have to specify a maximum recursion depth so that you avoid infinite recursion or infinite loops. I mean, it's a best practice to provide such loop terminating conditions. Otherwise, you may end up with an infinite iteration and infinite recursion, which may crash, likely crash your system.
I'm sorry,
So,
sir, my network glitch at the point, sir.
okay, I'm saying, okay, the two conditions for terminating our reflexive loop are one, the critique node is satisfied with the current draft. If the critique node is satisfied with the current draft, we don't need to do any reflection again. We just move ahead, persist in current drafting vector store and output it to the user. On the other hand, if the critique node is not satisfied with the current draft and we have not reached the maximum number of iterations that we specified, then we continue looping in the reflective, continue iterating through the reflective loop until either the critique node becomes satisfied or we exceed the maximum number of iterations that we specify. It's important that you specify a maximum iterations because if you remember last week, we talked about that as part of the best practices when we're talking about um, conditional edges and the routing function. We specify that you need to I mentioned that you need to specify maximum number of iterations to avoid getting into an infinite loop situation. We also mentioned that you need to specify maximum recursion and depth, as when you're using recursion in your agentic loop. But it's standard best practice to specify maximum recursion depth where you're using recursion, maximum iteration um, cycles where you're doing iteration, so that you avoid infinite loop or infinite recursion situations which could crash um, your agent. I don't know whether that adequately answers your question, does it?
Yes, sir. Thank you so much, sir. I understand.
Okay, you're welcome. So let's go to knowledge graphs then. Please let me know when you can see my screen.
Yes, finish up, sir.
Okay. So when we're talking about vector-based memory, um, just a moment, please. Excuse me. Okay, sorry about that interruption. Um, yeah, I was saying that when we're talking about vector-based memory, I mentioned that um, vector-based memories are, even though they capture, they are they serve well for when you want to capture similarities for correlation, but they do not capture the exact relationship between entities, right? Knowledge graphs help to,
Logic.
yeah, knowledge graphs help to close that gap. A knowledge graph memories, a knowledge graph really, it's made up of entities and the relationship between them. The entities are the nodes, and the relationship between these nodes are edges, right? It captures the exact logic, the explicit knowledge and logic. For example, you have things like citizen of, CEO of, located in. For example, in Abuja and Nigeria, they are related. If a vector database, in a vector database, Abuja and Nigeria will be they will be close to each other in the vector space, right? But that will show you that they are related. But what exactly is the relationship between them? A knowledge graph would capture that relationship. Abuja, capital of Nigeria. So this extra detail helps to avoid um, it helps to prevent hallucinations because it grounds the agent in a network of facts. When we were talking about orange and um
Lemon and tangerine.
yeah, orange, lemon, and tangerine. You see that orange, lemon, and tangerine, for example, they may be clustered close to each other in the vector space, right? That shows will show you that they are similar. Okay. Now, but what really is the relationship between them? The relationship is that they belong to the same family. So, okay, let's say citrus, orange and citrus, or citrus family if you care. So, orange, member of citrus family, tangerine, member of citrus family. Um, was it lemon, member of citrus family, right? If you just
Yes,
had
sir.
orange, citrus family, lemon, tangerine, all of them may be clustered together. But what really is the relationship? The knowledge graphs helps us to capture that relationship. So if you know that if there is an edge between orange and citrus family, tangerine and citrus family, lemon and citrus family, it means that from orange you have a link to tangerine through from the orange node, a link to the tangerine node through the citrus family node. And that way um, you can gain better insights on how these nodes, these entities are related. That I don't know whether that's clear enough.
Yes, sir. I'm just thinking around this, sir. I quite understand the very good advantage of the knowledge of graph memory over vector that you mentioned. But then I'm only trying to imagine if it's possible, or I know it could be possible that this relationship may change. For instance, the example of Abuja and Nigeria has been okay. Let me use the CEO for instance. If the CEO of a company, if the person changes, is there a way around it for updating this knowledge
Of
so
course,
that it will capture?
of course you can update the knowledge. Maybe in next week or in 2 weeks' time, you will see how to prune knowledge graphs so that outdated knowledge is fizzles out from the graph. So so it's possible
Okay, apart from,
to prune your graphs
I'm
to
sorry, sir,
remove
apart
outdated
from,
knowledge. Go ahead.
okay, I'm sorry, sir, apart from updatable knowledge that may change, the case of Abuja and Nigeria, for instance, is
Yeah.
it, I mean, I don't know, maybe the situation is near my warrant that the way Abuja relates to Nigeria, maybe Abuja can also have relationship to, okay, let me say Nigeria, then we have Abuja and Lagos. Because considering vector space, vector memory, I know Abuja and Nigeria will be close, like you said. Lagos too will be close, you know.
Yeah,
So I'm just trying to
Abuja,
look at it.
Abuja, Lagos, and Nigeria will most likely cluster together because I mean Abuja and Lagos are in Nigeria. But
Yes, sir.
what you can, or that all that's all you can get from
The knowledge graph. Now that's what I'm, how did it? The knowledge graph.
yeah, I know. I'm going from vector memory now. The vector memory will just cluster them together. They are related. But what is that is that relationship? Now, in your knowledge graph, you could capture the relationship between Lagos and Nigeria, for example, as Lagos is in Nigeria, it's a state in Nigeria. You can also capture Abuja is in Nigeria, right? That's similar relationship. But then there's also another relationship between Abuja and Nigeria. Abuja as capital of Nigeria. There's another relationship between Lagos and Nigeria. Lagos, former capital of Nigeria. So you could capture all that.
On knowledge graph.
Yes, you capture as much detail as your use case requires.
Yes, sir. Yes, sir.
So essentially, we'll also look at code to demonstrate knowledge graph memory. I'll stop sharing for a bit and so I can share my idea. Please let me know when you can
Yes,
see
it
my
just came up
screen.
now, sir.
Okay.
It just came up.
Okay. So, well, I'll just go straight to the meat of the code because the configuration is still the same we had in the code for vector-based memory agent. So here is where we'll start, where we set up our knowledge graph. For our knowledge graph, we're going to use network X. Network X, it's essentially just a graph. You have nodes and you have edges. Later in the course, we'll actually use an actual graph database, but for simplicity here, we are using network X to simulate the graph database. It's a graph, that's fine. So it just essentially becomes an in-memory graph DB. And so we define our knowledge graph using networkx.multi digraph. And we define the agent state. The only difference here now is that we are using a knowledge graph context to represent the information that we retrieve from the knowledge graph. We define a helper. We define a helper function that extracts entities, entity triples from from a given text. So given a text, it extracts a subject, predicate, and object, which is really the kind which models the data that is persisted in the knowledge graph. The subject is an entity, the object is another entity. The predicates represent the relationship between these two entities. For example, we talked about the Abuja, capital of Nigeria. Abuja is subject, Nigeria is the object, and the predicate is capital of. So something like that. This helper just extracts that kind of
Data.
structure, triple structure from any given text. It's a helper. So we go to our nodes. The first node is the knowledge graph lookup node, just like our extraction node from the um, vector-based memory agent. Um, so here we are using an LLM. Um, we are using an LLM to extract um, entities from a given text. The text in this case is a user query. So we extract the entities from the user query so that we can search the knowledge graph for any persisted relationships with involving these extracted entities. And that what that information that we retrieve becomes our found knowledge. So for all the entities that were retrieved here that the LLM identified from the user query, if the knowledge graph has a node containing that entity, then we retrieve that relationship as this string entity, which because is a source node. The predicate is the relationship. The object is the destination node. So return a string like that for um, every instance of that entity in the knowledge graph. Now, for all such strings that we're able to extract, we concatenate them into a single string that forms the context, graph context, which we will use to update the state as we return in the command object that the KG lookup node returns, and the next node will be the writer node. But assuming no such relationship was found from the knowledge graph, then it means that we don't have any relevant information from the graph database, and so we need to go search the web. We use targeted search. Therefore, the next node will be the researcher node, and we set the search query to be the user query, and the context we set it to be an empty string. The research node is, well, essentially is the same, similar to what we had in the vector database. The only difference here is that we're using a simpler, it's essentially the same thing, just call Tavili, concatenate what you retrieve from it as a string and use that to update the research data of the state, and then we go to the writer node. The writer node is still similar to that in the vector-based memory agent. The only difference is that we are using graph context here, which is the context from the knowledge graph. In the vector, um, in the vector-based memory agent, we just used what we retrieved from the vector database. Here we're using what we retrieved from the graph, knowledge graph database. That's all. So it's essentially the same thing. It creates that draft, and then we'll call the critique node as the next node while updating the draft of the in the state. And now the critique node is still similar to this critique node. The only difference between this and the vector-based memory agent is that where we had context from the vector store, in this case of the knowledge graph memory agent, our context is from the knowledge graph. So it's still just the critique node just determines whether the draft is accurately and completely answers the query, and then it provides a critique of that draft, assuming it sees some gaps in it, and then it also determines whether it's necessary to whether the information that context the agent already has is sufficient to um, is sufficient for rewriting the draft, or is necessary search the web for additional information. And then it also, where it's necessary to search the web, again, it suggests a more appropriate or a more optimal search query, and it also returns the JSON output of the same schema as we had in the vector-based memory agent. And so based on whether the critic node thinks that the current draft is adequate, or if we have exceeded the specified maximum revisions, then it goes to the node to save the relationships identified from that draft, persist it in the knowledge graph. But if neither of these conditions is met, then and it thinks that it's necessary to perform another web search, we go to the researcher node. On the other hand, if it thinks that the current draft is not adequate and we still have not met or exceeded the maximum specified maximum revisions, that means it goes to the writer node since it thinks since it thinks that the current context that the agent has is adequate, so there's no need to search for more information. The node to persist the retrieve the current knowledge that he has gained, from the draft, the relationship that he identified, to persist it to the knowledge graph. Simply, the logic is we extract triples from that draft. Remember our helper function that extracts triples of subject, predicate, and object. That means relation between two entities, where the two entities are the nodes and with their relationship. So that helper extracts triples from the current draft, and for each triple, it adds an edge to the knowledge graph, an edge between the subject and the object of that triple, where the predicate forms the edge. And here, this just brings that out to let us know that this particular relationship was persisted to the knowledge graph. And also, this indicates the current number of nodes and the current number of edges, which helps us track when the graph is growing. And of course, the final draft is printed out in this case, but you could output it in some other way in your own implementation in production. It could be by returning it as an API response or whatever. And so we define the graph. We are still using an edgeless graph, so there's no need to define edges except the stats to specify that the graph execution starts from the knowledge graph lookup node. And then we still invoke the graph async by using the async method. Now here, our first query, what our AI development is 2025, similar to what we had in the previous script where we used the knowledge vector-based memory. The second one, we ask about what is a similar query in this case. Yes, saying tell me about AI developments 2025. So it's similar to the first. The third one, we ask about something different. What's the latest news in Japan? Now, it's expected that where we where the user query is about something that is related to what's already in the knowledge graph memory, the model will pull that information from the knowledge graph and would not need to perform a web search since it has relevant information from the knowledge graph. But where there's no relevant information in the knowledge graph, where it's unable to retrieve relevant information from the knowledge graph, then it performs a web search. So let's execute this and look at the output. Okay, I wanted to be sure that we were using grok models because Olama models may be a bit slow. Okay, so the first time, definitely there would be no graph connection found since, I mean, we've just defined the graph, so nothing is persisted in it yet. And so it said it couldn't find any connection, and the KG context is an empty string. The search query is the same as the user query. So because it couldn't get any graph relevant graph connection, it performed a Tavili search, and if it retrieved the information, which I believe would include URLs, and so it creates a draft there with in the writer node, and it should also cite its sources. Oh no, in this case, no cite. There are cite. I think there are citations, but it didn't include URLs. And um, the critique. I think I've just a moment. Yeah, the critique doesn't think that that draft is. They say the current draft provides a general overview of AI development in 2025, but lacks specific details and examples. It touches on a blah 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 blah. So since it thinks this is not the draft is not adequate, and probably it also specifies that it's necessary to search again. It performs another Tabili search now with a new search string. This is the search string the critique notes suggested. It writes another draft based on the retrieved information from the new website. And from here, apparently, the critique node still thinks it's not good enough. It performs another search with a a different search query that the critique node suggested. And then this time is either, I think, how many iterations did we specify um, in the config? Yeah, we said maximum of 2 revisions. So here he has already tried 2 revisions. So since he has hit the maximum specified revisions, it terminates and uses that draft as a final um, report. And then this is a string showing us the relationships that are now persisted to the knowledge graph. Artificial intelligence witnessed significant advancement in 2025. AI adoption was characterized by enterprises. So, if for each of these triples, there is a subject, a predicate, and an object. And so it adds all these into the knowledge graph where the subject and object are entities and the predicate is the relationship between them. Now, for example, here where it says AI agents and AI maintenance, these are 2 entities, right? They are related. If we were just using a vector based memory, these will cluster together so that they are related, but it wouldn't give us the relationship between them. Now, here is explaining what the relationship is. AI agents created new job opportunities in AI maintenance. AI agents created new job opportunities in AI deployment. AI agents created new job opportunities in AI development. So this provides better information and helps to prevent hallucination because with a vector-based memory, once you know that this is related to this, the model can just okay. Here we have that AI agents as a node has edges with these 3. Now, with that means the 4 of them will be clustered in a vector space. And so, assuming they all have the same distance, the distance between each each of these three with AI agents is the same. With vector-based memory, when you are trying to retrieve um, information from a vector-based memory, any of these can be returned since it's the same distance. And so the model can use any of those in its response, even though that one may not be the most appropriate. But with the knowledge graph and knowing the exact relationship, okay, in this case, it's the same relationship. Let's look at something AI agents and tasks, AI agents and AI development. Tasks and AI development all are related to AI agents, but it's these predicates that clearly differentiates the relationship, and so it helps to ground the context that the model makes use of when it retrieves that information from the memory, and so helps to mitigate the occurrence of hallucinations where a model just outputs some information just because they are um, clustered together in a vector space, even though that might not be really the most appropriate information in the context of the user's intent. And then here we specify that with the graph size is now 53 nodes and 35 edges. Of this is essentially what the graph started from. This is the first time we are updating the graph, and we also output that final draft to the user. It includes references, but in this case, um, it did not add the web links.
URL.
Yeah, URL. Yep. The second query now, which is related to the first, it said no relevant connections found. I really don't know why, but then too, you also need to maybe in later classes we'll see how to um, rank the importance of the relationships that are found in the knowledge graph, so that only those that are ranked of high importance will get retrieved. But I guess as it keeps persisting that a specific information related to a search query, that information becomes more important and probably to retrieve it as being relevant. Anyway, essentially, we still repeat that process and we increase. See, now at this end of the second run, the number of nodes and edges have increased, and that is commensurate with the new nodes and edges that we have added. And we run the third query too, and it runs similarly to that. So essentially, that's our demo on knowledge graph memory based agent. I would like to ask that you try this yourself. Try with different queries. A first query, a second query that's related to it, a third query that's not related, and so on. Both the vector-based memory agent and the knowledge graph memory agent scripts. Just try them with different combinations so you get a good hang of how that works. Because as we proceed in the next couple of weeks, we will be building on these, and there will also be adding um, other categories of memory, including the episodic memory and the procedural memory. Do you have any question at this point?
Well, no, no, sir.
Okay, so in that case, I guess we'll call it a night, and we'll see you on Tuesday as we continue our discussion on memory in agentic AI. And next week we will start talking about episodic memory. So I'll stop the recording at this point.
Yes, sir. Thank you very much.
You are welcome. Mm. Okay, so I guess I'm no longer um okay. I'm still the host, so I can stop the recording. Just a moment.